We're going to continue talking about electromagnetic waves by considering today how do electromagnetic waves carry power and how do lossy materials affect them. So let's start with the lossy material stuff. Last time we came up with this wave equation, the Laplacian of the electric field plus the wave number squared times the electric field is equal to 0. And that's for lossless media. But if we want to know how this works in media where the conductivity is not 0 and it's not infinity, so like finite values of the conductivity sigma, we got to start back with Ampere's law. Now Ampere's law, when sigma is not 0, is sigma E plus j omega epsilon E, right, is equal to the curl of H. So this is our conduction current term. And this is our displacement current term. If you remember in the wave equation that we wrote for lossless media, K is omega times the square root of mu times epsilon. The easy way for us to work this out is to write a new wave equation where we replace sigma plus j omega epsilon here on E with a new complex value for epsilon. So we're going to write that the curl of H is equal to sigma plus j omega epsilon times the electric field, which is equal to j omega epsilon c times E. Epsilon c is our new complex value for the permittivity. It's an effective complex permittivity, and it has a real part, which we're going to call epsilon prime, and an imaginary part, epsilon double prime. Notice that there's a minus sign here. You'll see why when I write it out, because epsilon prime here is just epsilon of the material, so the normal material permittivity. But epsilon double prime is because epsilon c is equal to epsilon plus sigma over j omega. And as you know, when you divide by j, that's the same as multiplying by minus j. So that's why over here we have a minus j. So epsilon double prime here is sigma over omega. Now, if we put that back into our wave equation, we're going to get Laplacian of E plus j omega mu, that part comes from Faraday's law, times j omega epsilon c, which comes from Ampere's law, times E, is 0. And we define a complex propagation constant, gamma, so that gamma squared is equal to j omega mu times j omega epsilon c. So in lossy media, this is going to be not a purely imaginary number, it's going to be a complex number. So gamma is going to be alpha plus j beta, where alpha is our attenuation constant, and beta is our phase constant. Let me write a nicer beta for you. And that is the square root of j omega mu times j omega epsilon prime minus j epsilon double prime. So there's our new propagation constant in a lossy medium. When we have e to the gamma z, or e to the gamma whatever your propagation variable is, that's going to be, well, let's say e to the minus gamma z, so we're going in the plus z direction. That's going to be e to the minus j beta z, so it'll accumulate phase like it normally would, and then it's going to also have e to the minus alpha z, which is going to cause our electric field and our magnetic field to lose amplitude as they propagate along the direction of propagation. Now, this stuff is all true in general, and we can also define an intrinsic impedance for lossy media. Where that eta now becomes the square root of j omega mu divided by the square root of j omega epsilon prime minus j epsilon double prime. There are a lot of different ways to express these things, and just like usual, if you want to find the wavelength, beta is equal to 2 pi divided by the wavelength. So the wavelength is obviously not complex. If you want to find the phase velocity, you can find that using beta. All of that stuff works the same. But since we have in here, we have now complex rather than purely real or purely imaginary numbers inside of square roots, that makes our expressions for eta, for alpha and beta, for gamma, and for basically everything else a little bit more complicated. So there are some approximations that people can use for this, but they depend on the type of material that you're dealing with. So we like to sort materials into good dielectrics or good conductors. And the condition for whether you have a good dielectric or a good conductor is the relationship of epsilon prime to epsilon double prime. If epsilon double prime over epsilon prime is much less than 1, you have a good dielectric. If epsilon double prime over epsilon prime is much greater than 1, you have a good conductor. And in general, the decision point is you want about a factor of 100. So epsilon double prime needs to be 100 times epsilon prime if you want it to be a good conductor, and it needs to be 100 times smaller than epsilon prime if you want it to be a good dielectric. And in those situations, there are a set of approximations that we can apply if those things are true. So anytime we have a square root of the complex effective permittivity, that is a square root of epsilon prime minus j epsilon double prime. If it's a good dielectric, we can use the binomial series expansion for the square root of 1 plus x, where if x is much less than 1, the square root of 1 plus x is approximately equal to 1 plus x over 2. You see where I'm going with this now. Then the square root of epsilon c is actually equal to square root of epsilon prime times square root of 1 minus j epsilon double prime over epsilon prime. So far, no approximation has been made. But then I can make that binomial series expansion approximation and say that that is approximately equal to square root of epsilon prime times, look, there's no more square root, 1 minus j epsilon double prime over 2 epsilon prime. And then you use that expression in all of your other, in all of your calculations to get all of the other parameters. Now on the good conductor side, what we do instead is we have a lot of terms here. If we go to the same place as we did before, epsilon c is equal to epsilon prime minus j epsilon double prime, which means that you could have epsilon c equal to epsilon prime times 1 minus j epsilon double prime over epsilon prime. But if you have epsilon double prime over epsilon prime much, much greater than 1, then in general, this term is going to dominate over 1. So we just say that something like epsilon double prime over epsilon prime plus 1 is approximately equal to 1. Approximately equal to epsilon double prime over epsilon prime, and we ignore the 1 entirely. Obviously, that goes double if epsilon double prime over epsilon prime is squared, because now we have a factor of 10,000 difference instead of a factor of 100. It's hard to tell the difference between a double prime and a 4, but that is a double prime. I will write it very carefully. There you go. So, if we are making these two approximations, our new expressions for things look a lot simpler. Gamma on the good dielectric side becomes square root of j omega epsilon times square root of j omega, that's not an omega, omega epsilon c. No approximation yet, but we can say that that is approximately equal to j omega square root of mu times the square root of epsilon c, which is square root of epsilon prime times 1 minus j epsilon double prime over 2 epsilon prime. So now we have beta, which is this first part with the that gets multiplied by the 1. So that works out to be j, well, the j doesn't come out because beta is inherently the imaginary part, so it's omega square root of mu epsilon prime. And then it's easy to tell that alpha is omega, omega square root of mu square root of epsilon prime divided by epsilon prime. So epsilon double prime over the square root of epsilon prime. And if you remember, epsilon double prime is sigma over omega, so the omega cancels out. Oh, and there's a factor of 2 there, excuse me. So there you go. Now here's the thing. If you have an especially good dielectric, which most of the time if you're using the good dielectric approximation, it's fine to do this, you can see how the phase constant is actually the lossless phase constant. So beta, these are approximate, but the approximation for beta is that it is the lossless phase constant. The other thing that you can do is that you can say that the intrinsic impedance is also approximately the lossless intrinsic impedance, which would be mu over epsilon, square root of mu over epsilon prime. That's also the lossless value. Now, on the good conductor side, any terms that have 1 plus epsilon double prime over epsilon prime get replaced with just epsilon double prime over epsilon prime. So then our expression for, oh, and it's important to know a fact here, and that is that the square root of j is actually not approximately equal to 1 plus j over root 2. If you don't believe me, think about these in exponential form. J is e to the j pi over 2. So if you take the square root of e to the j pi over 2, that is e to the j pi over 4, which it turns out is 1 plus j over root 2, if you remember your sines and cosines. So anyway, anytime you take a square root of j, you get 1 plus j over root 2. So then gamma is approximately equal to 1 plus j times omega mu sigma over 2, and eta is approximately equal to 1 plus j times omega mu over 2 sigma. You can work these things out yourself, starting from the general expressions for gamma and eta that we got from the wave equation. All right, so that's lossy materials for you. You can classify them as a good conductor or a good dielectric and use simplified expressions for how they behave. There's one more important thing, and that is the value that we use to classify them, that epsilon double prime over epsilon prime, has a name, and it is called the loss tangent. It might seem weird to call it as a tangent until you remember that epsilon c is a complex number that is epsilon prime minus j epsilon double prime. So the tangent of the angle of epsilon c is, if that's the angle right there, I'm going to give it some, not even going to give it a variable. That's epsilon double prime, that's epsilon prime. So the tangent of that angle is this fraction. That's why we call it a loss tangent.